With Houdini 19, a couple of new things came in for Vellum, and one of them is what we will see in another video, Vellum rigids, but also Vellum fluids. So side effects realized they can actually do a simplified fluid simulation with Vellum, which allows you, as we've seen in the last video, to basically cover the most important simulation types and let them, in the context of Vellum, interact with each other. So how does that work with the Vellum fluids? You actually have a Vellum configure fluid menu entry now. And as you can see, this just creates a Vellum configure grain, actually, funnily enough, that with a type set to fluid. So this is basically a grain simulation with a couple of properties that a fluid follows. For example, fluid particles stick to each other. We call that cohesion, and that will make it feel like fluids. Of course, a Vellum fluid will not replace a flip fluid. It's way too simple for that. But for small scale or simple or maybe cartoony-like simulations, it's actually a pretty good solution. This is actually something you have seen in the video, in the example that I showed you. Especially the fluids don't really look like, as good as they could. They really feel CG-ish, and this is the problem that Vellum fluids have. But if you're not familiar with the flip system that we will look at in the next chapter, then this can be a simple alternative. So let's go a bit more practical here. So all you need really is some kind of input to the constraint that, just like a Vellum grain, will be filled with particles. Let's move this up a little bit. And I would recommend having a lot of particles to make this look good. So at least 2000 or something like this. So let's increase the particle amount by lowering the particle size, just like a grain system would work. And then you just connect this, of course, to a Vellum solver. And let's activate the ground plane. And when you run this, you can see it doesn't really feel that different to before. But that's because we still don't have enough points in here to make this really shine, and also we don't have a really good example case here. But let's run this again, and here you can start to see it a little bit better, that it starts to behave a bit more fluid-like. Now here's the problem with the system. Since this is grain based and all the calculation happens between the points, as you might have guessed, what the system needs is a lot of substeps. It already has a lot of constrained iterations here, but you will not get away without increasing the substeps by quite a bit. 5 is already quite low, but let me show you the difference already in the behavior. And what you can see is that it creates those clumps or those, pieces that stick together that almost feel a little more fluid-like now. One way of showing this a bit better is to add a little bit of a collision. So the first thing we can play around with is maybe adding just a box to see how it behaves when it collides. And here you can see it behaves a lot more like a fluid because particles stick together in a way that feels, kind of muddy, maybe you could call it. Here at the bottom you can see that. Let's actually increase the amount further. And while we're at it, increase the substeps. And the more points you add to the system and the more substeps you add to it, the more it will actually start to feel like a fluid. And here you can see that more and more of this behavior starts to come in. Now, one of the reasons why this feels a bit weird is that our blob of fluid currently is pretty big. Because when we look at Tommy, there he is, we have this massive blob of fluid, and it would actually take, let's move Tommy away a little bit, way more points to simulate this properly. To give this something that makes a bit more sense, let's make it a bit smaller, which also means we have to lower the particle size even further. And actually let's play around with a collision object that makes a bit more sense here. Like, for example, a glass. And I try to more or less find a scale that makes sense for this. There you go. So let's bring our sphere closer to this, also adjust the size even further. And I think at this point we don't need Tommy anymore. And lower the particle size further. And now I think we will be able to see that the system even can create splashes and stuff like that. It's a bit hard to see, to be fair. So let's get rid of the glass for now. But here you can see the behavior. And one thing you might want to do here is not just let this, certain amount of fluid fall into something, but let's constantly add more to it. And this is something that we already learned in the spawning Vellum geometry, because in the Vellum solver you just double click, and for that very purpose there is a source output. And here you just add a volume source, and like everything in Vellum, what you need are two things. You need the geometry and the constraints. So what you actually use for this is what we already created, this up here. And the best way of doing this usually is to split this up into maybe something like source geo and source constraint so that we can find it later. I usually turn stuff like that red. And then here we have to not only give it this source point, we also have to give it a source constraint. Very important. You need to bring in the constraints as well, as we've seen in the spawning video. And what will happen now is that this source that happened in the very beginning will happen currently, well, actually not, no, it will not. It will by default only happen once. So let's make sure we actually switch this to each frame. And now it will happen each frame. And then it looks like this. And you can see that there's more and more fluid emitted from this source and actually is able to fill our cup here. Again, what's really important here is to give it enough substeps. For something like this, I would even go as high as 20 or 30. And the logic, roughly speaking, is again that the longest collision chain will give you an indicator of how many substeps you need. Which doesn't mean you need 200 here, but you know, it has to do with the longest chain that you find in your simulation to define what is a good number. And here you can see that the fluid can fill something. So let's quickly have a look at this. And to make this better visible, let's merge the two together. And something I have prepared, because otherwise we wouldn't see anything, is a little shader here that will make our glass more transparent, and then we can see a little bit better how this would look like. And you can see, okay, we have a bit too many particles here. So it's a lot, too much volume basically, but you can see that this is actually possible. And now we can kind of feel the fluid-like behavior. Let's make our source a little bit smaller maybe. And let's run this again. And then you can see a bit better, you know, how this feels together. And you can see it feels kind of fluid-like. Now what's missing here, of course, is obviously we wouldn't want to render a fluid as points. And this is something we will talk much more about in the flip chapter, because this is a classical fluid problem. But you know, as a little hint into the future, what comes next in one of the coming chapters is there is actually a node taking care of this called particle fluid surface as one possible option. And the thing you have to remember here is that it has a particle separation to understand basically how the points behave relative to each other. And this, in our case, is the same number as the particle size. So let's copy that and paste it in here. And now it will interpret those points and mesh them to a geometry that we can render as a fluid. And if we give that some kind of fluid material, maybe some whiskey or something, then it looks like this. And yes, this is not mind-blowing. It will look much better when it's rendered. But as you know, viewports always have problems with refraction, so transparency is not very kind to a GPU renderer. Nonetheless, it looks a bit closer to what we can expect later on to be, you know, the look that we will get from this. And when I flipbook this, because obviously that's pretty slow, partly because the particle fluid surface is relatively slow, then it looks like this. And you can see, you know, simple fluids you can actually simulate now with Vellum, and it doesn't really look like a Vellum simulation, right? It looks a bit more like a fluid sim from the 90s, right? So this is what you've seen a long time ago, and this is what I meant. This is not really meant for realistic rendering of complex fluids, but for small, maybe cartoonish stuff, this can be actually pretty fine. Now let's talk about a couple of other things that we can do with that, and one of it is viscosity. And why not just keep the example that we have here and just move our glass to the side a little bit so that our fluid will collide with it properly, something like this maybe. And we want to turn this into honey. Now viscosity is a topic that we will talk again in the flip chapter, because it's a pretty important topic about that. Basically, what is viscosity? It's how thick a fluid is. And this is actually built in the Vellum fluid, among other things. You have density. This is important for when you interact with other objects. It's basically the mass. So it's all about the energy transmission between objects. We talked about this in detail. Then the phase, that's only important when you mix fluids. So if you have multiple fluids, let's say water and oil, then you can let them have a different phase and then they will not mix with each other, which is pretty interesting that you can do that. But what we're interested for now is the viscosity. Now, if you set this to 1, you will not see much difference to before. You have a relatively, you know, fast moving fluid, let's call it. But if we want something like honey, what honey has is a pretty high viscosity, like 200. Now, this is something we will see later on. The viscosity numbers can go really high. They can go into the hundreds. It's not 2 or 3 or something like that. In Flip, they even can go to the thousands. But in Vellum fluid, I noticed that this is roughly the number that feels similar to honey. And it's not without problems because we now get a staggering problem. But nonetheless, when you look at the behavior of the fluid, it's much thicker now, much slower in the behavior. And also the points will stick together much more. So this is more like, you know, a thick fluid, maybe honey, maybe, I don't know, something like chocolate or something, hot chocolate. Something that, you know, is more viscous, we say. So let's run this for a bit. So after a bit of time, and that's the problem of the system, it is slow the more points you add to it, much slower than Flip, by the way. But then it looks like this, and you can see it behaves, yeah, like, you know, a thick viscous fluid, maybe, you know, too thick for honey. And it looks even better when you run this through the shader. Again, looks even better when, you know, it's not in the viewport, but you get the idea. You can even simulate this kind of stuff. Let's flipbook this again. So, you know, again, we have staggering problems, and, you know, the realism is missing to a point. It still feels very CG, and that is the core problem with it. But nonetheless, you know, it was relatively simple and quick to set up, even though the simulation time was pretty abysmal. I don't want to go deeper into this because there are better sources for this. I just wanted to show you what's possible with the system. There is even a way of calculating surface tension, which is another topic we could look into. But, you know, this is more about giving you an overview. One last thing I want to show you is the big advantage of the Vellum fluids. And as we talked about, that is interaction with other Vellum setups. So what I have here is pretty straightforward, actually. We have a planar patch, and I actually activated the top seam so that we can use that in the Vellum cloth constraint that we need, of course, to pin the upper points in the air. And because I like colors, I turned it red, nothing special. Then I Vellum pack so that I can merge it with the other one, and that is more interesting. That is a sphere here that I turn into a fluid with a Vellum fluid, which is actually a Vellum configure grain, as we've learned. And I haven't changed much here other than the particle scale. And I made sure that the seed is changing every frame, as you can see here, so that the source is constantly changing. Otherwise it will look a bit boring. And then I gave it a start velocity in the direction, of course, of our cloth here. And then I added, like we saw before, to constantly emit new fluid to this, a Vellum source that takes the exact same outputs that come from the Vellum fluid node here up there, including the velocity. And that results in a constant stream of new points that are flowing, so to say, in the direction of our cloth. And that is really slow to calculate. So after quite some while, it looks like this. So, you know, let's stop this emission after maybe a couple of frames, maybe here, after the first 10 frames, because this is really what we care about. I mean, you already see, you know, what I meant is this is actually a bidirectional reaction. So the cloth is slowing down the fluid and the fluid is slowed down by the cloth. So it goes in both directions. Let me quickly make this more interesting by stopping it at some point. So actually we could even stop here maybe. So this is pretty easy because the Vellum source, exactly for that reason, has an activation up here. So we can make sure that this will stop if the frame is higher than 5. No, wait a minute, it will stop. It will be activated as long as the frame is lower than 1005, actually, in my case. This then will be activated, and after it, this condition will not be true anymore, and this way we can turn it off, okay? So let's wait for another 10 minutes to simulate this. So here we go. That was faster because we only have fluids for a certain while. And yeah, There's not much to say about this. You can see there is now a full interaction. It took a long time. And of course, like I said before, what we would do here is, as I said, one way of turning this into an actual renderable fluid mesh, you can use the particle fluid surface using the same particle size as our fluid setup. And then you can see that it looks a bit more like a fluid. Actually, we have to, I'm afraid, split this up. I should have created a group for that, but well, so be it. So yeah, here you can see both elements. Yeah, so here we go. It's a bit fast, so I had to slow it down, but you know, you get the idea. Bidirectional interaction is possible with the fluid and the cloth, and this is actually something that was really hard to almost impossible. So yeah, that's Vellum fluid. It's basically a grain system with cohesion. So that means you can use the Vellum configure fluid node. And what you see then is that this actually creates a grain setup set to fluid. And this will then behave a lot more like a fluid because particles basically try more to stay together. What you can do with this is not as good as a real flip simulation, but much simpler to set up. And for certain things, there is no alternative. And that is when you have to interact with other Vellum systems, for example. But for really large scale simulations and so on, it's way too slow. And after all, it doesn't look very realistic. So be careful when using it, but there are certain cases where it's good enough, let's say. So yeah, that much about Vellum fluid, just so that you have a rough overview when to use it and roughly what it's capable of. So I hope this is helpful. Thanks very much and see you later. Cheers.